First of all, I would like to thank the organizers for organizing this conference and giving me a chance to present my work. I'm going to talk about the index of Diffie-Hellman mapping, which is based on a joint work with Arne Winterhoff. First, I'm planning to talk about the index, what index of a mapping means, and what do we mean by Diffie-Hellman mapping. And let me move. First, before giving the definition of index, I have to give some terminology and actually talk about first cyclotomic cosets. We have a multiplicatively written finite cyclic group G with order n, and we take the generator. I have to go to here. We have the generator gamma for our group G, and L be a positive divisor of n, then the set of L powers is a subgroup of G of index L. Then the elements of the factor group, the elements of this factor group are called the cyclotomic cosets. As you see here, we can call this coset like zeroth coset of G, and each I, we get the ith coset by multiplying the power of gamma to the G with this, the zeroth coset, and they are all called cyclotomic cosets. And for any positive integer r, any L element of G, we define the rth order cyclotomic mapping. We use this notation of index L. We define it by this. So what does it mean? For each element from the ith coset, for each element x from the ith coset, the image of this element is defined as x to the r times ai, where ai is the element of group. And what is index? We still didn't say it. So my keyboard doesn't work somehow. For a self-mapping f, the smallest index, such that our f is defined in this way, we call it the index of f, and we use this notation. Okay, so and this is again self-mapping, but now our group is multiplicative group of finite fields fq star. If we have a self-mapping f over fq star, we know that any mapping uniquely written by a polynomial of degree at most q minus 1 with constant term 0 by Lagrange interpolation. So who first defined this index? Well, I would also like to say about it. The index of a polynomial over fq with constant term 0 was first introduced by Stephen Wang in 2007 with this paper, which was actually based on the work of Niederreiter and Winterhoff paper published in 2005. And if you would like to look for further references, one can actually check this paper of Stephen Wang, which is quite recently written in 2019. It's a survey paper about index. So we can ask this question, why are we interested in this index of a polynomial? Well, the answer is because we would like to find unpredictable polynomials which are necessary for cryptographic applications. We need unpredictable polynomials. Any mapping of small index is highly predictable, and any mapping of large index is needed for cryptographic functions. And now I have to say about Diffie-Hellman mapping. As we know, one of the most common public key crypto system, Diffie-Hellman crypto system, is based on the assumption that the secret key gamma to the AB, to recover secret key gamma to the AB from the gamma to the A and gamma to the B. So the security of the Diffie-Hellman key exchange is based on the assumption that infeasibility of evaluating gamma to the AB from gamma to the A and gamma to the B is over a group G is actually invisibility of evaluating this Diffie-Hellman mapping. That's how I can say it. So we call this the bivariate Diffie-Hellman mapping, which is defined in this way. And this is actually can be efficiently reduced to the univariate Diffie-Hellman mapping. So which we also define it in this way. So for small d, I use for the univariate Diffie-Hellman mapping notation. Capital D is used for the bivariate Diffie-Hellman mapping. So this is univariate. So we can, this bivariate can be reduced to the univariate in this way with this short calculation. So if you take the square of the bivariate Diffie-Hellman mapping, you see that it is actually calculated. The right-hand side is obtained by the univariate Diffie-Hellman mapping. Here, this square roots in group G can be calculated by using the Tonelli-Shanks algorithm. And in I add these references. If somebody is interested in, they can find out in the Bach and Schalitz paper in 1996. So, okay, I would like to state the first theorem. We have a cyclic group of order n with generator gamma. The index of the univariate Diffie-Hellman mapping over G is n if n is odd, n over 2 if n is even. So here we can conclude that actually the Diffie-Hellman, the univariate Diffie-Hellman mapping D cannot coincide with a small index mapping, not at all points of G. They don't coincide, not all points of G. Points, I mean elements of G. Even with the following theorem, we can see that. So let me first state the theorem. The univariate Diffie-Hellman mapping, the cyclic group G order n coincide with any mapping of index L in only exactly these elements of G. So this is actually small set of G. So we can say, we can conclude here that the univariate Diffie-Hellman mapping D can only coincide with a small mapping of G, not many points of G. So if n is prime, we have a better bound 2 times L. So our index is the coincide elements are at most 2L. We can say that. And this was the univariate Diffie-Hellman mapping case. And for the bivariate Diffie-Hellman mapping, first I have to define the index pair. So what does index pair means? We have a cyclic group order n. Now we have two positive divisors of n. Let's call them L1 and L2. For two positive integers R1, R2, and L1 times L2 elements from G, it looks a little bit complicated, but the idea is similar with the univariate case. So we define the R1, R2 order cyclotomic mapping with this notation with index pair L1, L2 by this. So here again you see that the pair X and Y are respectively coming from this coset and this coset. Then their image is defined in this way. K1 and K2 are 0 to L1 minus 1, L2 minus 1, respectively. So the index pair is called, if we have a mapping satisfying this property, then this L1, L2 is called the index pair of F. So, and then I'm going to state the result about bivariate mapping. Bivariate Diffie-Hellman mapping. So this is the Diffie-Hellman mapping for the bivariate case. The bivariate Diffie-Hellman mapping has only index pair n, n. So this is our result. But we also look at how many points of G square can this bivariate Diffie-Hellman mapping can coincide any index L mapping. So any mapping of index pair L1, L2 coincide with the bivariate Diffie-Hellman mapping of the cyclic group G order n at most this amount of elements of G square. And now we also look at the special case of G, such that if G is a subgroup of multiplicative subgroup of FQ, I mean FQ star, if G is a subgroup of FQ star order n dividing Q minus 1, again gamma is our generator of G order n. So this is the result. Our F is over FQ star self-mapping, satisfying this. This is, as you see, that it can be induced to the theorem. This is induced to the univariate Diffie-Hellman mapping. But here, our S is a subset of this set. N is integer, H is integer. And S has cardinality H minus S, and H can be maximum n. Then we have this lower bound for the index of F. Here, if S is 0 and the n H is n, S is 0, then we are reduced to the theorem 2. This is for the multiplicative subgroup of FQ. And this theorem 2 implies index of F much greater than the cardinality of S divided by square root of n for any S. And if you see that this lower bound does not exist square root of n, however, theorem 5, this one, oh, sorry, this theorem 5 provides larger bound better than square root of n for any S satisfying the condition which are stated in theorem 5 with this condition. So it gives a larger bound if we have this condition. And we do the similar ideas for the bivariate case, bivariate Diffie-Hellman mapping. So if G is a subgroup of FQ star of order n, n divides Q minus 1, and G is a group generated by gamma, U be any subset of 0 to n minus 1, and V is a set of this. Again, n is an integer, H is an integer. As you see that here, the cardinality of V is H. For some H less than n, and we have bivariate mapping F G cross G to G. It's any mapping of index pair satisfying this. This is the, again, bivariate Diffie-Hellman mapping if they are coincide. Then we have this result. Maximum of L1, L2 is greater than minimum of cardinality of U and H. Here actually H is cardinality of V. We can also write a minimum of cardinality of U and cardinality of V. So it's really about we are checking the coinciding with the Diffie-Hellman, bivariate Diffie-Hellman mapping with any mapping satisfying this. Then we have this result. This is also the theorem 4. Where was it? Let me remind it. This one, the theorem 4, which says that bivariate Diffie-Hellman mapping of order n at most, they coincide at most this amount of elements of G square. So this, if you apply this here, sorry, my keyboard is a bit strange. Yeah, here, if so we had maximum of L1, L2 is greater than minimum of kernel of U, kernel of V. So if you apply it, we see that the right-hand side is always smaller than square root of n. So that's why this theorem 6 provides a lower bound, which is greater than square root of n for any U and cardinal, for any U and V, I can say also V here, satisfying minimum of cardinal of U and cardinal of V, which are greater than square root of n. So we use some technical, the proofs are a little bit technical, some calculations are technical. We use, for instance, character sums in most of the parts. And in the proof of theorem 2, we use the result in this paper, the number of solutions. At some point, we had to use this to find the number of the solutions in the congruences. And in the theorem 5, we use the result, the lemma 1 in this paper. And this idea is coming from the Sparlinski, these notations. Let me, yeah, here,
Leyla,
theorem, yeah.
Leyla, 2 minutes.
Yeah, I'm checking. Thank you. I'm almost done. And theorem 5, here these notations S and H, these definitions are actually based on the Sparlinski's book, here, this book. And yeah, the theorem, we also use the main theorem in this book. These are the, I can say, summarize the references that I used, we used in the proofs of our theorems. And that's all I wanted to say. Thank you so much for listening me. I hope I was able to explain.